Our next speaker for today is Professor Gesa Hartwigsen. She is here. She has a background in psychology and is currently professor for cognitive and biological psychology at Leipzig University. And she is also heading the Lise Meitner research group, Cognition and Plasticity, at the Max Planck Institute for Human Cognitive and Brain Sciences. Her research focuses on the adaptability of the language network to different challenges such as lesions, aging, or non-invasive brain stimulation. And that is what she will talk to us about today. So Professor Hartwigsen, thank you for joining us, and you have the floor.
Yeah, thank you so much for the invitation. I'm looking forward to this. Can you hear me and see my slides?
Yes, we can hear you, and the slides we see in now full screen.
Good. Great. Yeah, so thanks again. You already said everything about my talk, and I think we have a nice connection to the question that was just asked, namely about neurostimulation in the brain. So what I want to present to you is something about the plastic language network, how we can study functional plasticity in the language system by using non-invasive brain stimulation. So when one thinks about language and how language is represented in the brain, then the first important issue to consider is that language is organized in networks. So there is not just one language center in our brain, but language engages distributed networks. So this is work from a meta-analysis that includes hundreds of neuroimaging studies from the last decades, and that shows essentially that we see language representations across language comprehension, production, different tasks, mainly in the left hemisphere, but also engaging right hemispheric areas, subcortical regions, and the cerebellum. Now, when we look further into detailed components or different linguistic operations, such as the processing of the meaning of words or its semantics, or the processing of the sound of words, the phonology, we see that different specialized subnetworks contribute to different functions. And successful communication, when we talk to each other or listen to each other, requires flexible interactions between such specialized subnetworks. And the big question that I'm interested in is how the language network then adapts to challenges. What do I mean by that? So what I want to find out or unravel is the flexible adaptation in our brain to challenges in the language network across different brain states. In healthy young brains, challenges can naturally arise under demanding listening conditions, for example, at train stations or at the airport. But we can also artificially perturb our brain with inhibitory neurostimulation to build models how the brain or the language network adapts to that we then can transfer to aging or lesion brains. In aging brain, it is an ongoing debate which of the changes that we observe as we age reflect dedifferentiation, so the overall cognitive decline, and which of these changes may be beneficial and reflect compensatory adaptation to changing conditions and maybe less cognitive power. And finally, in aging brains, I'm very interested in changes due to successful recovery of functions, for example, after brain lesions such as stroke or brain tumors. So in essence, I want to uncover common mechanisms of flexible adaptation across or from healthy young to aging to lesion brain. Now, one method to study this is non-invasive brain stimulation. And when you look at the history of non-invasive brain stimulation, especially transcranial magnetic stimulation, then it comes with a strong promise of causality, especially in the field of cognitive neuroscience. So the promise of causality, or the ratio for this, usually works as follows. The idea is that I target a specific brain area, for example, a language area, with an inhibitory neurostimulation protocol, and this should lead to a measurable change in my task performance, for example, during a language task. So the idea is that if I apply my brain stimulation protocol over this area of interest, and I see a change in task performance, a decrease in the task accuracy or an increase in the response latency, this proves that this area is causally relevant for this task. And hopefully I would show that this is specific for my language task, but not just any response to the neurostimulation. So the naive ratio that is often used in many neurostimulation studies in the field of cognition is that causality can be inferred if inhibitory neurostimulation over area A significantly affects task performance in task X, but hopefully not in task Y. This is, of course, much too simple, which is illustrated here. So the simple, I stimulate, I see a change in the response. This means this area is directly relevant for the task performance ratio is much too simple because there are several influence factors at several levels, both at the level of function, at the level of spatial distribution and temporal distribution, and at several levels of our brain organization. So for example, these includes physiological parameters. The individual brain morphology or the head anatomy will strongly influence how my neurostimulation protocol, and this applies to all neurostimulation protocols for non-invasive brain stimulation, TMS, TDCS, TACS, also for focused ultrasound stimulation. So the individual head anatomy and brain morphology will interact with my effect and will also define how strong my effect may be at the site of stimulation. Same holds true for things like the oscillatory brain state, if I'm in the rest state, if I'm during a task. And some of these factors are controllable, but others are unknown and often simply ignored. The same holds true for the methodological parameters. These are usually easier to control. I know which stimulation coil or device I want to choose. I know how to define my protocol, but I don't know how this will interact with my task of interest. And finally, the cognitive properties also play a large role, which is often neglected. For example, we see a large amount of functional plasticity or compensation when we target several areas. This is something that I will address a lot in the next minutes. And also it depends the outcome will depend on the type of your dependent variables, so which outcome measures you want to choose. So in essence, the take-home message is that neurostimulation protocol effects, especially for non-invasive brain stimulation, depend on numerous internal and external variables. They all interact, they will all influence my outcome, so what I can measure, my task performance, and some of them are hard to control. And one way to get more insight of what we are doing and how we are actually influencing the brain beyond just looking at the changes in behavior is to combine neurostimulation with neuroimaging or EEG. And what I want to show you is how we use neuroimaging as a readout to map our stimulation effects. So the idea here is that I apply plasticity-inducing non-invasive brain stimulation, TMS, TACS, TDCS, and then map the after effect of my neurostimulation protocol. Usually the protocols that we use have after effects in a range of 30 to 45 minutes. And then I can, for example, inhibit a language area and then map the induced changes at the network level with fMRI. And this gives me insight into what is called short-term reorganization or adaptive plasticity. That is how the brain responds or adapts to a focal perturbation. And the idea is that the combination of neurostimulation and fMRI allows me to quantify the impact of neurostimulation at the neural network level. I can investigate changes in task-related activity, changes in task-related interactions, and associate them with the induced behavioral changes. So I get a better idea how the network responds to a focal perturbation. So what do we know from such approaches in the language network on how, or what do we know about adaptive short-term plasticity? This means the immediate response of the brain to a single perturbation. This is an overview from a recent review where we summarized different studies in the language system and also on auditory cognition. And they have one thing in common. They targeted a key area for language in the left hemisphere, and afterwards put the healthy control subjects to the MR scanner and measured the induced changes of the inhibitory stimulation on task performance. And what we see here is that after perturbation of a left hemispheric language area, we see a strong upregulation of homologous areas, so the same areas in the right hemisphere. And this is often taken to reflect compensatory activity increases after disruption of the dominant hemisphere. So after disruption of the dominant hemisphere, the right hemisphere, or the non-dominant one, shows more activity to maintain task function. And I have summarized these and other TMS fMRI findings in a model that should explain, or might explain, how flexible adaptation in the language network may work. And this model has two key assumptions, namely that adaptation can either take place within the specialized language network, or it can also engage networks across the language network, so beyond the language network. So how should flexible adaptation within networks look like? Let's assume we have a simplified language network shown here, and we target one of these areas with inhibitory non-invasive brain stimulation, which is often referred to as virtual lesion. Now, this will decrease the contribution of the targeted area to my task because I inhibit this area. And now, in turn, the other areas of the network may show an upregulation, so a stronger contribution of the task, stronger task-related activity, which would point toward a certain robustness of the network. Alternatively, or additionally, we sometimes also observe a shift of the functional weight towards other areas of the network. These may be areas that did not strongly contribute before the perturbation, but are unmasked in their contribution and now play a stronger role. And finally, as illustrated before, we also often see an upregulation of homologous areas. So in case of language, mainly the homologous areas of the right hemisphere. And the idea is that such flexible adaptation within the specialized language network is highly adaptive and helps to maintain task function at a high level. Now, in some cases, we have large-scale disruption if we target specific densely connected nodes of the language network. So in such cases, the larger language network is inhibited and the areas within the language network cannot compensate for the perturbation. So in such cases, what we sometimes observe is the recruitment of alternative networks. This could be neighboring networks for other specialized functions. For example, during reading, we know that there are several pathways for reading. And we also sometimes observe the recruitment of domain general networks. Domain general functions such as attention, cognitive control, or working memory are known to contribute to all higher level cognitive processes. And the idea is that if the specialized language network is perturbed, stronger recruitment of domain general networks may help to some degree to compensate for the disruption. This is not to suggest that domain general functions can replace specialized language functions. They can't, otherwise stroke-induced brain lesions wouldn't have any consequences. So one question that we're currently addressing is if such flexible adaptation across different networks is a general or generic mechanisms that we observe across different brain states. So my model is mainly based on data from healthy young subjects with neurostimulation, but do similar principles also apply for aging and for lesioned brains? If so, then this model might explain how the brain adapts to lesions and could also be used as a starting point for therapeutic applications of non-invasive brain stimulation. So what do we know about flexible neural network recruitment in aging brains, and especially the role of domain general networks here? As I said, it is still hotly debated once we age, which of the network changes that we observe reflect adaptation and compensation, and which of the network changes are rather reflecting the overall cognitive decline. So to address this is work by my postdoc, Sandra Martin, who's interested in neural reorganization in the aging language network. So she used fMRI in old and young subjects and a very simple verbal fluency task to see how executive speech functions engage different networks. And she found that increased interactions in domain general networks is associated with better behavior in older adults. What does that mean? Here you can see the difference in task-related activity during verbal fluency. So this was a semantic fluency task participants view categories, and they have to come up with members of the category and have to overtly produce them. And we generally see that older adults have increased task-related activity relative to young subjects in domain general areas, in particular the right IFG and some of these more domain general midline structures and superior parietal lobe. Older adults also show increased task-related interactions between different domain general networks. So here, for example, we see the interaction between a seat region in the right insula. This is part of the multiple demand network for cognitive control, and the default mode network. And finally, we see that increased interaction within the domain general multiple demand network, so this network for cognitive control, is associated with overall better executive functions. So this gives us a clue that some of the changes that we see, so more contributions of the domain general networks in aging brains, seem to be associated with also better executive performance. But what about language? So can we also relate these changes to better language performance? So to address this, Sandra recently reanalyzed her data, and she found that older adults also show increased facilitatory network interactions, which are associated with better verbal fluency performance, so not just executive functions. So to show this, she used an independent component analysis. So she used her task-related activity and extracted the underlying patterns of the different networks that contribute. And this graph may look complicated, but the main conclusion that can be taken away from this is that in aging brains, we see increased facilitatory network interactions between task positive and task negative networks. So these are the networks that in healthy young brains are usually anti-correlated, such as subnetworks of the default mode network and the ventral attention networks. So overall, it seems that older subjects show more positive network interactions between domain general networks during verbal fluency. And these interactions, the direction of the interaction changes from young to aging brains. And these changes seem to be behaviorally relevant because facilitatory network interactions are associated with better semantic fluency selectively in old brains, whereas the opposite pattern is found in young brains. So it seems that we have a different strategy in aging brains to be able to perform the same task. And this is also shown here. So we finally used a graph theory analysis to look more into these network interactions. And with such analysis, you can create graphs of the network interactions between the different networks. And you can see that the graph for the older subjects looks a bit different from those of the young subjects. And we focused here on a measure which is called segregation. This means how much networks form specialized communities. And we see that older adults show significantly decreased segregation, so less specialization of the networks and more between network interactions. And we finally found that a high level of segregation or specialization of the networks is associated with better language accuracy and better executive function, so better overall performance selectively in the young brains. And so this shows that indeed we see differences in the strategy, more between network interactions and less segregation of the networks as we age. And these are these measures, this between network connectivity is associated with better task performance selectively in aging brains. And this brought us to the idea that we can explore the potential of facilitatory neurostimulation to domain general regions to improve performance. And this seems to be the case, but for the sake of time, I will not focus on these data. So now we know a bit how plasticity during language or flexible adaptation may look like in healthy young and aging brains. But one question that we are also very interested in is how does this look like in network disorders? Which role do domain general networks play in network disorders? And one network disorder is dyslexia. So this is a learning disorder characterized by impaired reading and writing. And this is work led by my postdoc, Sabrina Turka, who focused on aberrant network interactions during reading in adults with dyslexia. So we had a reading task again performed during fMRI, and the subjects had to read words or words without meaning, that is pseudo words of increasing complexity. And you can see here that the adults with dyslexia perform worse on almost all measures. So they have overall longer speech onsets, they also have longer speech durations, and decreased or impaired reading accuracy, at least for the more complex pseudo words. Now the question is, so this is nicely in line with the literature, but the question is, what are the neural correlates of such impairments? So we contrasted the task-related activity of control subjects with people with dyslexia, and we found that the adults with dyslexia show an underactivation, so less activity in the extended reading network, which was associated with the impaired performance. What does that mean? They show less activation in classical reading areas of the left hemisphere, like the left supramarginal or ventral occipitotemporal cortex, but also the right VOTC and the right cerebellum. So during the same task, they have less activity. Also, this is nicely in line with the previous literature. We then focused on the network interactions during reading, and we found the same pattern, namely that between the areas that showed less activity, these were used as seed regions, and we looked at the task-related interactions with the rest of the brain. And between these underactive regions and the rest of the brain, we also see massive hypoconnectivity. That is, decreases in the task-related interactions between areas of the reading network, many domain general areas, and many other brain areas of both hemispheres. And the strongest pattern you can see here down on the right panel below is for the right cerebellum. The right cerebellum showed massive hypoconnectivity with almost the entire brain. So this leads us to the idea that dyslexia is maybe best characterized by underactivation and hypoconnectivity in the extended reading network and beyond, so including classical reading areas, right hemispheric areas, and also domain general areas. And the next, the first conclusion is dyslexia can be best characterized as network disorder. And the next question that we were interested in is if we can improve task performance and what the impact of facilitatory neurostimulation will be on network activity, network interactions, and how this relates to induced behavioral changes. So when one thinks about application of non-invasive brain stimulation to improve reading in adults with dyslexia, this has already been done in a number of studies as summarized here in this review article. And usually therapeutic applications also for people with dyslexia require repeated applications of different non-invasive brain stimulation protocols over different areas. So usually these studies target classical reading areas, also sometimes areas for visual processing, and also one study targeted the auditory cortex. And some of these studies report significant improvements after NIPS application over one of these key areas. What remains unknown is how this affects task-related activity and connectivity. So what are the neural underpinnings of these induced improvements? And to address this, we used transcranial magnetic stimulation, so facilitatory TMS with a protocol called intermittent theta burst stimulation. And we only applied one session to look at the immediate changes. This was not a therapy study. So we targeted the left temporal parietal cortex, so the area TPC here. And you can see here, this is a simulation of the current flow that with the stimulation protocol, we targeted the area that we aim to target. So more red or more pinkish here means that the strongest current flow was induced in the area that we wanted to target. And we also found that a single session of this facilitatory TMS protocol improves performance, at least complex pseudoword processing. So we also had a main effect of stimulation, but it was driven by the complex pseudowords, so by the most challenging condition. So we have improved accuracy and increased task efficiency for complex pseudo-word reading after TMS relative to placebo stimulation. Now, what happens at the level of task-related activity? Here, we did not find anything at the stimulated area, but only some induced changes in remote regions of domain general networks. So when we looked at changes in task-related activity with standard analysis, we found significant modulation of the precuneus. This is an area of the default mode network for word reading, and significant changes of the right insular and neighboring auditory cortex in the right hemisphere for pseudo-word reading. So it seems that facilitatory TMS can change task-related activity in remote domain general areas, but no effects directly under the coil. We were very surprised to see that, but it's not uncommon. Not all TMS studies find something directly under the coil. And then we looked at changes in functional connectivity. So we used seed regions from the predefined reading network and also found that TMS decreases the functional coupling between remote areas of the reading network and domain general areas. So TMS over this TPC areas changes the connectivity between other areas of the reading network and domain general areas. And it was interesting to see that we see a decrease in the connectivity. One might expect that the connectivity should be increased here. And finally, to zoom more into the reading network, we took the areas of the predefined reading network in the left hemisphere, a very simple model, so left prefrontal cortex, ventral occipitotemporal cortex, and the target site in the temporoparietal area. And we used an effective connectivity analysis here with dynamic causal modeling. So this should give us an idea how the brain areas of the reading network are influenced by the facilitatory stimulation and how they change their connectivity during reading. And we found, what we found was as follows. We found that ITVS, so this facilitatory stimulation, indeed increases the facilitatory effective connectivity in the reading network. And we see especially increased connectivity during pseudo-word reading. So when it gets really challenging, that was stronger after effective stimulation relative to placebo stimulation. And that was found not between the stimulated area, but between the other nodes of the reading network. So this was slightly unexpected, but nicely shows that that we indeed see stimulation-induced changes at the network level during reading induced by facilitatory stimulation. And this was correlated with more efficient processing. So the stronger the increase in the connectivity between these areas of the reading network, the stronger the speech onsets after TMS, or the stronger the facilitatory stimulation effect on task efficiency. So it seems that ITVS improves reading performance and decreases connectivity between reading and domain general areas, but increases facilitatory connectivity inside the reading network. So this may indicate that the way how TMS here works and improves reading is by increasing the connectivity inside the specialized network and decreasing the contribution between reading and more domain general regions. Now, finally, I want to say a bit about flexible neural network recruitment in lesion brains and the role of domain general networks here. Why is this important? This is important because we know that brain lesions such as stroke often severely affect language function. But how the language network recovers from stroke is still not fully understood. There are different theories about the role of the language network itself, the contribution of right hemispheric areas, but also about the contribution of domain general areas. But it's not clear yet which of the changes in the activation really contribute to good recovery. So this is a study that was led by Annika Stockert from Dorothee Sauer's group here at Leipzig University in the Department of Neurology. And she focused on the role of domain general regions in language recovery across the time course of recovery. What does that mean? She had patients with lesions either in the temporal, parietal, or frontal cortex, and they were investigated longitudinally. So after the stroke, they were investigated during the acute phase, the first days after stroke, the subacute phase, the first weeks to months after stroke, and in the chronic phase, that is after 6 to 12 months. So the subjects had to come, or patients had to come 3 times. They were put into the scanner and had to perform a simple listening paradigm. So they listened to sentences, and this was contrasted against reverse speech. And we found very interesting patterns, and I will focus here on the changes in the relatively early changes in task-related activity in those patients with posterior lesions. So they had lesions in their temporal parietal cortex. And what you can see here is the changes in the task-related activity when they listen to speech from the acute to the subacute phase. So after the first days relative to the first weeks up to 3 months after stroke. And what is striking here is that we see early increases in task-related activity in bilateral brain regions. Many bilateral prefrontal brain regions, such as the left and right insula, the right dorsolateral prefrontal cortex, but also midline structures such as the supplementary motor areas. And these are areas of different domain general networks, including, like for the SMA, this multiple demand network for cognitive control. And now, interestingly, this was also related to better task performance or language improvement. So you can quantify the amount of language improvement with neuropsychological test batteries. Here we use the standard battery that is the Aachen aphasia battery. And we found that at least in patients with brain lesions in the temporal parietal cortex, an early upregulation, so stronger activity from the acute to the subacute phase after stroke in domain general prefrontal areas, so left and right insula, right dorsolateral prefrontal cortex, midline structures in the SMA, is associated with better language improvements. So with improvements in the language scores in the aphasia battery from the acute to the subacute phase. So this shows that also in patients with brain lesions, early contribution of the domain general networks seems to be associated with better recovery, seems to be beneficial for recovery. Oops. And finally, what we are looking at now is how the neural reorganization in the lesion language network may look like at the network level. So far, we have seen the pattern of task-related activity, but we also wanted to understand in the same set of subjects or patients how the different areas interact with each other and how this changes across the time course of recovery. So this is work led by Zhizhao Yang from my group, who's doing her PhD on this project. So she looked at the data from the 2 groups of subjects, either with frontal or temporal parietal areas, and focused on task-related activity, connectivity, again during listening to speech when controlled with or contrasted with reversed speech. And Zhizhao now extracted the areas where we showed changes in task-related activity in the study before and looked at task-related network interactions. So here you can see the model. The model includes preserved areas in the left IFG or PTL, so posterior temporal cortex. These were extracted on an individual patient basis. So for each patient, we took those areas or those voxels in either the left IFG or PTL that were undamaged. Then we included 3 domain general areas from the multiple demand network, left and right dorsolateral prefrontal cortex and the supplementary motor area. These were the areas that showed the strongest early increase in task-related activity. And finally, we also included the right IFG because it is still hotly debated if the changes or this early upregulation of the right IFG during aphasia recovery is adaptive or if it's maladaptive, so just reflecting disinhibition after stroke. And here the question was, how does the interaction between these domain general and the language areas change across the time course of recovery, and which of these changes are predictive or associated with good language behavior and recovery? And I want to focus on a very first finding that I found very interesting and intriguing. So this is the model, the winning model, so the most likely model that explains the connectivity early after stroke, namely in the acute phase, that is in the first days after stroke. And what we see here is that we see increased facilitatory effective connectivity from the domain general areas, so the midline structures and right and left DLPFC, to perilesional language areas, so those areas in the temporal and inferior frontal cortex that were still undamaged. So it seems that already very early on, we not only see increased task-related activity, but also connectivity from the domain general network to the language network. And this early increase in the connectivity was correlated with better preserved language performance. In the early phase, of course, we don't have a recovery score because the early phase, the acute, is the first measurement point. But we see that selectively in patients with temporoparietal stroke, an early increase in the connectivity from domain general multiple demand cortex regions to the language area, namely the PTL, is associated with better preserved performance. So it seems that early increases in the facilitatory influence of domain general areas on perilesional temporal cortex, so on the preserved temporal cortex, is associated with better language performance. And I think this is very interesting because it nicely complements our previous studies where we also showed a relatively early increase in task-related activity. Here we can show that the increase in task-related connectivity may even play a role earlier, directly in the acute phase after stroke. And we are also currently investigating how this changes across the time course of stroke and how these changes are related with later better recovery. And the idea or the first findings is that these results are also relevant for language recovery. So increased connectivity between domain general and language specific areas are also related to better outcome, that is better language recovery. So this leads me to the summary of my data. So what do we know already about flexible neural network recruitment during language processing, and how can this be summarized? So I guess everyone would agree that neural networks must remain flexible to adapt to challenges. And one core aspect of such flexibility seems to be the contribution of domain general areas that we observed in healthy young brains, in aging brains. We observed that it seems to play a role in network disorders such as dyslexia and during language recovery after stroke. So we see that neural network interactions change as we age. And the big question for the future, or also our current work, is to dissect those changes that reflect compensatory patterns, so are adaptive for maintaining behavior, and those that reflect dedifferentiation or the overall cognitive decline itself. We have some first ideas based on our data that increased demands seem to require more domain general contributions and more domain general network interactions. So when healthy elderly participants perform the same fluency task as young adults, to be able to have the same pattern of accuracy, they need more contributions from domain general networks. And one idea that we're currently exploring is if facilitatory neurostimulation may target such domain general networks rather than only language specific ones to optimize network interactions and performance. If so, this might turn out a helpful therapeutic strategy that could also be used to counteract cognitive decline in aging, and that may be transferred to lesion brains. And finally, we also have some ideas that neural network adaptation is crucial for network disorders and language recovery. So we found that dyslexia, a learning disorder, can be best characterized as network disorder, at least in adults with dyslexia, which is described by massive hypoactivation and hypoconnectivity that is decreased overall or less activity and connectivity in adults with dyslexia relative to control subjects. We see that ITBS, so facilitatory TMS, seems to improve reading performance, at least for complex pseudowords, by modulating large-scale network interactions, both within the reading network and between the reading network and domain general networks. Domain general networks finally also contribute to language recovery after stroke. So we have good reasons to believe that especially an early recruitment of domain general networks may be associated with relatively preserved performance and also with good initial recovery. And especially what we now found is that early increases in the facilitatory connectivity of domain general on language-specific regions are associated with better language performance. And I think that's it for now. So I'm looking forward to discussing these results with you. Thank you.
Thank you very, very much for this amazing talk. I would like once again to encourage our audience to submit their questions via the Q&A. And we already have one question here, which I will now read out. It's a bit longer, so it's going to take a bit longer. So this is from Bernardo, and he says, "What an amazing and enlightening presentation. I have a very similar question regarding the role of frontal operculum adjacent to Broca area in the modulation of transitivity and efficiency of intrinsic functional networks in the context of cognitive reserve. The active model of resilience in senescence and neurodegeneration. The left operculum in the left frontal cortex is hypothesized to play a role in compensatory network mechanisms, such as maintaining small world properties and efficiency in network interactions, executive network control, DMN attention network, and salience network. My main question is the verbal fluency and involvement of language networks facilitating transitivity and network efficiently by recruiting resources, or is it an epiphenomenon of these network efficiencies?"
Wow, quite a tricky question. Yeah, I'm not sure if I can fully answer it. I think to fully answer this super interesting question that I find really, really good, what we need to do would be to extract the signal directly from the left operculum. So the areas that we found being engaged in or put differently, we also looked at connectivity changes in specific seeds that we took from differences between old and young subjects in task-related activity, but we didn't specifically focus on the left operculum. We had the IFG in there, but not this area. I guess the left operculum would be covered by the large-scale networks that we correlated with each other. But here, the value that goes into the connectivity analysis is an average weight across the different areas. So I think to really answer this question, what I would need to do is to check this area and extract the connectivity or the time series from this area and directly correlate it with other nodes from the network, and then see and then check with correlation analysis if this is associated with efficient and accurate task performance. At the moment, for me, it's hard to say. I think both explanations could be true. So it could also be just an epiphenomenon of the network efficiency that results in such changes. So yeah, it's interesting, but I have to say I could have a look at it. Yeah, but I didn't do it so far because it was not one of the most obvious seeds that were found based on our activity data that motivated the connectivity. Yeah, but thanks for this great question, and sorry that I don't have a more conclusive answer here.
No, thank you very much, and thank you, Bernardo, for the question. So then I will go on to the next one. Catalina is asking whether you can provide examples of how neurostimulation has been used to study and enhance functional network plasticity, and what are the potential future applications of this technology in cognitive enhancement and rehabilitation?
This is also a very good and very interesting question. So I know a number of studies. I think I had some on this brief overview slides for dyslexia treatment. And usually these studies, or the majority of studies, focus on anodal transcranial direct current stimulation. So the idea is that anodal TDCS, so with the active positive electrode being put over the target area of interest, for example, a language area, should facilitate task performance by changing the plasticity in the stimulated area or network and increasing the likelihood that the cells will fire. And I know that there is a number of studies that successfully applied such protocols during different language learning paradigms and also during aphasia recovery. So, for example, one fascinating study by Markus Mainzer's group, they used anodal TDCS over the primary motor cortex in patients with stroke-induced brain damage, also of frontal regions, and they found that anodal stimulation was associated with better language performance after stimulation. So that anodal TDCS of the motor cortex resulted in improved language performance after the therapeutic application. So I think this is one intriguing direction that has been tested in stroke patients, also in language learning in older subjects, and also in healthy young subjects. Another idea is what we tried here, this intermittent theta burst stimulation. So you can also use facilitatory TMS protocols. The problem is with all these protocols, the way how or their direction of their effect is usually taken from the motor system. So in the motor system, we can directly infer this if a protocol is facilitatory or inhibitory by looking at the changes in the induced motor excitability. Whether this always also translates to higher cognitive function is still a matter of debate. And that's why many of the studies that try different neurostimulation protocols for therapy are not really conclusive. And often, even if they find effects, the effect sizes are so small that it's hard to say if it will become clinically relevant. So what I think what we need to do is to better understand the nature of the neuromodulatory mechanisms. So how does this not only affect behavior, but also the underlying network interactions to identify probably the most efficient protocol for a specific language task or for a specific impairment. Yeah.
Yeah, thank you very much, and thank you for saying that. I had been actually wondering for quite some time how you determine whether a protocol is facilitatory or inhibitory for higher cognitive functions, and that answered that questions as well. And I think also the next question that we have in the chat, this also relates to therapeutic approaches. So I would say this is also answered. I do have one more question as well. So also because you mentioned smaller effect sizes because of stimulation. And this is a more general question about the intersubject variability that I'm assuming you also observe. So different people respond differently to stimulation. Some of them might improve, some might actually get worse. And I wanted to ask, first of all, whether there are any individual subject characteristics that might predict how someone will respond to stimulation, and also what would be approaches to improve stimulation to get better results in everyone.
Yeah, that is a fantastic question, and I wish I knew the answer, because I mean, here I only presented some interesting results where things worked out, but we have a lot of studies where we actually found null effects or super high inter-individual subject variability. And exactly like you said, some subjects show improvements, some show impairments, the majority centers around 0. And there are some ideas also taken more from the motor domain, which of the characteristics should be taken care of to, or which subject characteristics can explain such variability. And one important factor, I think, for cognitive studies is the individual baseline level performance. So from the studies that are out there, it seems that sometimes the same protocol can either facilitate or impair performance depending on your baseline performance. So for example, if you are already performing at ceiling and you apply a facilitatory protocol, then you might not see something at all. But if you are maybe in a medium range, the same protocol may have facilitatory effects. And some studies more in the visual domain suggest that if you are a poor performance, then the same protocol may even have the opposite effects. And similar results were found for old and young brains. So sometimes a protocol that has one direction in young brains has a different direction in the aging brain. And why is this? Because the overall state of plasticity, or also homeostatic plasticity, so the balance between excitation and inhibition in the brain, changes as we age. And the problem is, and this is exactly your question, how do we know this beforehand? And I have to say, from all the parameters that have been discussed, like individual motor cortex excitability, is this a good factor that also predicts responsibility for cognition? I'm not so sure. Then some genetic factors or levels of different polymorphisms like the BDNF factor have been discussed, but also here the results are not so conclusive. So I think this is maybe exactly the question for the next decade or so, that we find out which factors really define the individual responsiveness to a certain protocol, so that we can also better select the appropriate individual protocol when it comes to therapy. So I think, and here we should go to or follow two avenues. One way is to identify the factors that influence or that influence the individual variability and select those that can define probably responders and non-responders. And the other direction would be to use more individualized approaches. So maybe the idea that all the patients need the same approach is simply wrong, and we should move more towards personalized medicine and identify individual lesion patterns, and with the lesion patterns probably decide, oh, this patient might benefit more from stimulation of the language network, this patient may benefit from stimulation of domain general networks. And so far, to me, these or which of the factors are really relevant is absolutely unclear. One idea that we have based on our data is that we should, when it comes to therapy, at least in post-stroke aphasia, we should definitely consider the time course of the intervention. So it seems that early after stroke, we may need to target right hemispheric homologous areas and domain general areas with facilitatory protocols, whereas later in the time course of stroke, we may need at least to inhibit the right IFG. This is what some TMS studies in stroke have shown, and stimulate more the remaining perilesional areas and probably domain general areas. So the idea is that we may come up with an individualized approach that also takes into account the time course of the individual recovery profile. But I think it is too early to identify more specific factors that really play a role. So one is definitely lesion site and lesion size, and the other one might be the time course of the recovery. But which of the factors are already relevant in healthy young brains? So baseline level, performance, age, individual genetic profile, it's a complete mystery to me still. Yes.
Thank you very much for your extensive answer. Yeah, I asked because I also work with SOTDCS in older adults, and I was curious because we see the same thing. Some people respond to it, some people don't, and we are also pretty much at the loss as to why that happens.
Yeah, I think we're probably still in the area where we need to report such findings and check with the existing literature how we can explain them before knowing in advance what to expect, right? I mean, this is not so satisfactory, but someone has to do all this work, right?
Of course, of course. All right. Thank you very much again. If there are no other questions, then, oh, there's one more question, very quick. So Catalina is asking, can the principles of functional network plasticity and systems plasticity be applied to the development of artificial intelligence and machine learning models that adapt to changing cognitive demands?
Oh, good question. Brilliant. I don't know. I think what we could use machine learning models for at the moment, and what is being used, is to apply such models to large scale data sets to extract more common patterns or general patterns, for example, of network recovery. I think that this is done at the moment, but if this will help to to use a model that can really inform therapy, then I'm not so sure yet, because I think we first need to understand what these changes that we observe, or these pattern changes, mean in these large cohorts, and then transfer them to individual brains. But it's definitely an intriguing area and an area worth investigating, I would say. Yeah.
All right, thank you. And perhaps one final question before the lunch break. Since you mentioned personalized therapy approaches, do we have the technology for it now? And how can we make it accessible, since it will probably be more costly?
Yeah, that's also a brilliant question. So I know from depression research, because TMS is approved for depression treatment and seems to work, that one idea is that instead of using task-related activity, which is super hard to do and costly in each patient, one could rely on individual resting state connectivity profiles, which may be easier to achieve, probably also more in the clinical routine, and target areas that are densely connected hub regions in specific patients. So yeah, I think one idea would be to rely on resting state connectivity. And if this is even too expensive, one could also think about resting state profiles in EEG, which is much cheaper, or once we have more data available, define based on the existing data, identify good targets that then can be just used in the majority of patients that show specific impairment profiles. So come from the other side, come from the behavioral impairment, and say in other studies, this was associated with the connectivity profiles like this, and we found that targeting this specific node was beneficial. Then one could even probably reduce the costs. But so far, I think resting state fMRI to investigate network or identify network hubs might probably be a good option here. Yeah.
Yeah. All right. Thank you very, very much. Again, thank you for the wonderful talk, for the discussion, and for being with us here today.